Welcome to the Math Corner.
Don't you just love primes?
Prime ribs?
No, prime numbers.
Why should we even care about prime numbers, Taylor?
Well, Jenny, prime numbers are natural numbers with only two positive factors being 1 and themselves.
I mean, yeah, but what does that mean to me?
I mean, they're not composite, and 1's not prime.
Okay, what else?
2's the only even prime.
Again, why should I care?
I mean, cybersecurity, cryptography.
Could you elaborate more on that, Em?
Sure. Prime numbers help us encrypt pretty much everything. The first ingredient required for an encryption algorithm are two large prime numbers. The larger the numbers, the safer the encryption.
How so?
Take two very large numbers that are relatively prime and multiply them together. That way, it's hard to find the resulting number used to encrypt personal information because the only factors are the primes and 1.
But yeah, how's that safer though? Well, can anyone detect primes?
Yes, they can, and let me show you.
This is Euclid's proof for the infiniteness of primes. It'll come in handy later, so keep it in mind. Now on to primality tests. The most simplistic in my opinion is to take your number n and square root it, then check to see if any of the integers between 2 or the square root of n evenly divide your original number n. If they do, then n is not prime. Let's do an example with the number 54,321. The square root of this is somewhere around 233.06, so we have to check the integers between 2 and 233. That could take time, so let's learn a couple of divisibility checks to make this process a little less painful. The first thing I did was divisibility by 2 or 5. For this, I took the last digit. If it was a 0 or 5, it's divisible by 5. If it's an even number, it's divisible by 2. In this case, we have a 1, so we're good. Now, divisibility by 3 or 9. You take all the digits and add them together. In this case, we get a 15. Not divisible by 9, but it is divisible by 3. So that makes our original number automatically not prime. But let's keep on going for the sake of education. The next thing I did was divisibility by 7. This one is the trickiest one, but the funnest one. You take your last digit, double it, and then subtract it from your number. In this case, we get 54,319. Now, you take 9, double it, and subtract it from your number. And you keep doing this until you get a number that is obviously divisible by 7, or obviously not. In this case, it's not divisible by 7. Now on to divisibility by 11. For this one, you take all of the digits and alternate the sign between them. So add 5, subtract 4, add 3, subtract 1, or subtract 2, and then add 1. In this case, it's a 3, so not divisible by 11. But remember, our original number was divisible by 3, so it's still not prime. This is a JavaScript program we created to detect primes in pink and twin primes in blue, which are prime numbers that neighbor each other. Remember that proof of infinite primes from earlier? Well, a big question is whether twin primes are also infinite. So see, there's still a few unknowns, and despite massive efforts, there is truly no efficient formula for factoring large numbers into primes. Modern encryption algorithms exploit that fact. Also note, most individuals looking for primes are mathematicians, not hackers. So in essence, your personal information is still relatively safe.